Good afternoon and welcome to the sixth installment in our webinar series about how to use LabVIEW with the FTC competition in Tetrix Robotics. I'm again joined with my colleague Greg Sullivan.
Hello.
And on behalf of ourselves and our friends at National Instruments, I'd like to bid you welcome. We'll start off with a quick review of the previous webinar, in which we talked about a few new programming concepts that were necessary to create a little bit more sophisticated autonomous code. We talked about shift registers, we talked about the not Boolean function, the select function, and we took a quick tour of creating some solution code inside our autonomous framework to create some behavior using these functions. As we recall, shift registers allowed us to shift data from one iteration of a loop to another, essentially giving us the ability to remember information. They're always attached to loops, and the color and the data type matches automatically the type of wire connected into them. They are always a pair of terminals, one on the left side, which is an output, and one on the right side, which is an input. And the way we used the shift registers in last week's webinar was to use it to remember the direction of motion, so that whenever a particular occurrence happened, we would change directions. We're going to expand on the use of shift registers in this webinar to include a more sophisticated data structure called the state machine. We also talked about the not function, which has the simple behavior of inverting a Boolean value. So false becomes true, and true becomes false. We also talked about the select function. The select function returns the value wired into either the top or the bottom terminal, depending on the value of a Boolean wired into the middle terminal. And just a quick reminder of the goal from last week's webinar task was to perform a robot function that every time an object moved within 10 centimeters of the ultrasonic sensor, it moved in the opposite direction of the previous movement. The first time this happens, the robot would move forward. And if nothing was directly in front of the ultrasonic sensor, the robot would stop. And the robot would terminate when a touch sensor is pressed. This was the flowchart, which we programmed using the structures that we've just seen. In this webinar, we're going to take this a step further and come up with and discuss and then implement a data structure called the state machine. The state machine has several benefits, one of the most important of which is that it's easy to debug and easy to modify and extend, and we'll see that as we proceed. Basically, a state machine breaks up a robot's action into a series of modes, or states. And decisions are made as to what actions should be performed next. That decision is made on information provided in the current state. And state changes are generally made based on the values input by sensors, as well as other information collected throughout the program. State machines are implemented in LabVIEW by creating a case structure within a while loop. And whenever we've seen a case structure up to this point, it's been used to select what code runs based on a criteria. And one of the methods of using a case structure is to use a string to define which case runs. That's exactly what we're going to use in this implementation. We're going to be using strings to define which state is to run. One of the benefits of this is it makes it really easy to distinguish between states, as they can be given very descriptive names. Before we get into the implementation of a state machine, let's talk a bit about a state diagram. Basically, this is a way to document and plan our state machine. It's a visual representation of how a state machine should behave. It shows program flow using arrows to represent transitions between states, and it uses circles to represent the states themselves. Transition arrows are often labeled with an action that happens during the transition, or an input which triggers a transition. So here's an example. Here we see an example of a state diagram, which, as mentioned, is a way to visualize a state machine. Another term for that is pseudocode. So here we have a clearly labeled start and stop states. This is the beginning and the termination of your program. The start transitions into the first state, and you can see there's an arrow transitioning from the first to the second state, and then transitioning to the stop case, or the stop state. This is a very intuitive diagram. In fact, it seems kind of trivial. And as we'll see, the benefit of that, the natural progression of flowing from state to state to state, actually makes envisioning our programs easier and implementing them much more simple. So in this webinar, our goal is to write a program that once it detects an object, moves forward for 1 second, then moves backwards for 1 second, and then goes back to a state where it's checking for an object again. Further to that, when a touch sensor is pressed, it will actually stop. So let's think about this. Before we start going into LabVIEW and creating the code, let's think about the solution state diagram. Well, in order to start off, we're initially waiting for something to happen. So a very common usage of that is a state called an idle state. So the first part of our state diagram has us going from the start state to an idle state. Next, what we're doing in the idle state is we're checking for an object to be detected. So we have a transition from the idle state when object detected occurs. And we label that on the arrow. So the idle state goes to the forward state. So far, so good. The next step of the code was, after moving forward for 1 second, to then move backward for 1 second. So again, we have a transition arrow going from the forward state to the backward state, and a transition label on there saying after 1 second. That defines the decision that's being made. Finally, after the backward state has been occurring for 1 second, we then transition back to the idle state so that the whole code can execute over again. So we see here a very cleanly labeled and very cleanly understandable state diagram. The only piece that's missing is finally to respond to a touch sensor. If the touch sensor is pressed in any part of the program, it should then enter the stop state, which would allow it to terminate. And because we want that to be allowed to happen from any one of the states, we actually create 3 arrows leading to the 1 stop state. So still, even though we've added more functionality, our state diagram is very short, very easy to understand. So let's now go into LabVIEW and implement this state machine.